thank you, Gio, for that warm introduction. As you can see, Gio has come into the forefront as one of the leads of this local community here. And you can see he's developed a very good managerial skill. For every compliment you give somebody, take them down a notch as well. So this talk is, we'll see where this talk goes. I'm a little bit worried about if it's going to shape up in the end, but hopefully we'll show you something interesting. I first came to this event, the first year it was run when it was on the floating barge, the boat, and I gave a talk about adding the print statement back to Python 3. And it was kind of a joke talk, and it was something I threw together at the last minute, and I thought, well, this year I want to give a talk about something useful. And so I spent all my time trying to do something useful and ran out of time to actually put it together into a talk. And actually collecting the data for this talk turned out to be very difficult, but you'll see the general idea here. But in order to motivate this, what I wanted to do is I wanted to take something I'd worked on a long time ago that when I showed to people, they looked at it and they said, that's really weird. Like, what on earth is that? And they thought it was kind of fun. And then show how some of these techniques aren't just for fun, they're actually useful. So let me show you something just kind of cool. And we'll do it with just, so I'm just going to start a Python interpreter. And you're going to see that I'm starting a Python interpreter that I have here myself. I just built this myself earlier. This is like the latest version of Python. It's 3.7b4. So it's what will be released in probably another couple months, maybe even shorter than that. And you can see I have a simple example, and I can do things like add numbers. And in this path Python interpreter, I added a little thing called setRwatch and setRwatchF. And if we look at the help text for this, the help text is really unhelpful because if it even pops up, some of this gets really slow. But, oh, and sometimes it's seg faults. You know, this was done in a rush, but I'll show you. From sys import setRwatchF. And it's a function that takes a couple of arguments. And I won't even tell you what those arguments are, but I can do something kind of interesting. And you don't know what this does yet, but we'll talk about this in a second. And maybe some of you have even seen this before. Okay. So we'll go back. There's a normal Python interpreter, and it has like the number 1, and it has, you know, x equals 1, and what's 1 plus 1? It's 4, it's 8, right? And if we say x equals 2, and we say what's 2 times 2? It's 64, right? So we can do some kind of weird things by patching the interpreter, and we can look at this and we can say, what on earth is going on? You've fundamentally changed the way Python works. You've turned the number 1 into the number 2 into the number 4, and when you add 2 plus 2, you'd think that's 4, but it's actually 8, and you can do all sorts of really crazy things. And the behavior, you know, if we change that little rwatch function to do some random stuff, we could really cause someone to have a really bad day. But the question is, how is this actually useful? And so I wanted to revisit this idea and another idea that I talked about at PyData Berlin 2 years ago, called the quarks problem. And I'm going to show you a problem that almost all of you have run into in your real lives. How many here use pandas? How many here use matplotlib? So in pandas, we have like the series object, right? And the series object has an apply function, right? Let's look at the help text of that apply function. Can somebody tell me all the arguments that the apply function takes? No, it's got this star quarks. And if we read through this help text, we don't actually know what can be passed in there. We know some of this stuff can be passed down, but we can't really tell, like, what are all the possible arguments. Many of you use pandas, and if you look at the help text of pyplot.plot, you have the same problem. Star arg, star quarks, but in this case, they've at least tried to be kind of helpful. So if you scroll to the bottom of it, it'll say the quarks are these properties. And if you look at the documentation online, they actually hedge it a little bit, and they say, let's see, it's right here. They say, here are a list of available properties, but this isn't even the exhaustive list. So we don't really know all the arguments you can pass in, but here's some of them that we think you kind of can, that have worked and passed, that I'm sure if you're copying the code from online somewhere, maybe somebody would have done that. And if it causes an error, well, there's Stack Overflow, right? In some cases, it's even worse. Like if you look at a lot of these functions, you know, this takes a star quarks. What on earth, like, could those parameters be? There's almost no documentation here. And let's talk about why this happens. Because anyone have an idea why this pattern might exist and why this pattern might be very common to these two libraries, pandas and matplotlib, and many other similar libraries that we use in data science?
Because if you want to add additional parameters later on.
Exactly. So the problem is, if we think about these two libraries, one of the things that typifies these two libraries is that there is a very complex, hopefully consistent engineering core, and then lots of layers of conveniences. Matplotlib is a prime example. Nobody here wants to manage the Matplotlib draw tree. It's just too inconvenient, it's too clumsy. So instead, we use pyplot, and pyplot takes 3 arguments. You know, when you pass the color, you just pass like a single letter, like G or R, and it figures out what the actual color is from that. You know, if you do a hist, it does a lot of work in the background. And so what you see for a library like Matplotlib is a core that is very consistent and very mechanical, and all the mechanics are worked out very nicely. And then this layer that is incredibly critical to actual users of convenience functions that just call all that stuff. Now, if you think about it, if you were the author of a library like that, and you had some core function, and that core function took a bunch of arguments, and then you had some convenience function on top, you don't want to hard code these arguments. Why not? Because somewhere inside, you're going to be doing something like this, and every time this core changes, you'll have to change the convenience layer. And the problem is, the convenience layer probably changes much more often. It's much more reactive to user requests or user desires. It's much more reactive to different ways that people use this library. So you want to find some way to avoid adding in this dependency. Well, the problem is, when you do this, you completely remove the dependency. Now this convenience method takes any argument spec and just forwards it along. And so you're free to change this core function as much as you want, as long as the users correctly use this function here. And presumably some of these arguments, when you add them, would be given optional parameters, and so nobody's code would break. Now, if we think about a library like Matplotlib, remember some of these libraries, in addition to having this convenience layer, also have the property of being so fundamental to so many people's work that they can change only very slowly. And so the way that Matplotlib looks today may be fundamentally how Matplotlib looks in 3 or 4 years. And if you talk to the Matplotlib core developers, one thing that they will tell you is their timeline for how long this project will exist may be 15, 20 years. And so they have a lot of serious considerations put into how do we design this library so we don't arbitrarily break code, and so that we don't arbitrarily have to chase after changes made at this convenience layer or changes made at this core layer and how they affect each other. Now, one thing that you can think that's problematic from a documentation perspective is so let's say, you know, they're just, maybe we just say they're kind of lazy, so they didn't do this. So the problem is, if we had documented these explicitly, and then we had added a document here, or we had removed an argument here, documentation's wrong. So we still have a dependency, and we still have a dependency at the code layer. It's not a dependency in terms of what the arguments take or what they don't, but there's a dependency in terms of every time this changes, you have to change this documentation. And which do you think is worse? Like a code problem, like if you hard-coded the arguments here, and you got it wrong, you didn't update something, then some user is going to use it, it's going to break, they're going to go to GitHub and say, I hate you, you're stupid, you're ugly, this broke, why can't you do this right, you open source people are useless. People on GitHub aren't very nice. But they'll complain, and they'll complain very loudly and very quickly. And your test coverage might also help you. But if you create this dependency in the documentation, how long could bad documentation survive where the documentation of what the arguments are and what the library actually takes do not match up? How long could this sit unnoticed with users constantly saying, well, hold on, I tried this argument, because not everyone's going to use every single one of these arguments. So somebody in the middle of nowhere, let's say it's 3 a.m. because they went out drinking with Ian Oswald and Vincent last night, and then they had to put a talk together, and it's 3 a.m. and they're struggling to put their talk together, and they try to call a function, and oh, the documentation says this, but it's actually wrong. It's a very likely possibility. So we have a problem here where there's fundamentally, through these mechanisms of having a convenience layer and a core layer, an inability to reconcile them and to keep them up to date in a way that doesn't add a lot of human effort and also doesn't break a lot of user code. Now, one of the problems that we face is that you could say, in this particular pattern here, there are patterns where we can avoid this. I'll show you an example. The common decorator pattern looks something like this. And I'm sure many of you have written decorators before. So it looks something like this. So, and then maybe this is a decorator on top of some core function, and you decorate it, and this does, who cares, right? And we know that there's one thing that we are encouraged to do every time we write a decorator to avoid this problem of, if we run this code and we look at the help text of core, we'll see that it's the help text of inner, right? It has the args and the quargs. And we're told there's one thing we should do whenever we do a decorator in order to solve this. What's that one thing we should do? Functools.wraps. So from functools, import wraps, and then we should just do wraps f. And with that simple little thing, the help text for this decorator function looks normal. And so we don't have this problem anymore. The thing is, does anyone know how functools.wraps actually works? It's a very, very simple mechanism that is not in any way extensible. What happens is, it just sets an attribute called wrapper, and in PyDoc, when it generates the help text, it just follows the chains of the wrappers to figure out what's the innermost wrapped function. And so this functools.wrap really only works in the case where you're doing like a decorator pattern. I think it's functools.wrap, sets maybe wrapped. It only works when you're in this, yeah, see it's there, and actually I just want to print this out. So I'll show you the wrapped function. So it only works in this very limited circumstance. So as a general mechanism to avoid this problem, functools.wraps or similar approaches really don't work. Because typically with these convenience functions, the pattern that you see is you see multiple core functions. Like if you think about something like pyplot.hist to generate a histogram, right? It's calling a bunch of internal matplotlib core functions, and your hist function probably looks like, probably takes like one of these arguments, another one of these arguments, then star args and star quargs, and then it probably does like core 1 with some stuff, and then core 2 with some stuff. And so this wraps technique won't work. And you can think, well, one thing you could do is you could maybe create some like documentation helper that says, you know, forwards argument to core 1 and core 2, and you do some mechanism like that, but this is going to be really invasive. One of the goals of some of the techniques that I show in my talks is to identify what can we do in a very minimal fashion in, let's say, 3 hours before you have to give a talk the next day that could potentially be useful with a little bit of extension, but that do not require you to substantially rewrite code. How do you do these kind of things surgically? One thing that's very popular in the Python community these days, and I can say that I'm on the fence with regards to it, is static analysis. There is no such thing as useful static analysis in Python. Even for real libraries like matplotlib, it breaks very, very, very quickly. Let me tell you what I mean by static analysis. Many of you are familiar with PEP 484. Anyone know what PEP 484 is? Type hinting. And you will think that, well, you know, if we can do things like type hinting, you know, if you think about type hinting, it's kind of this idea that you set the type hint and you can track statically this argument gets passed to this, and if this was passed in as an int, we can check this as an int over here. But the thing is, one very important qualification that a lot of people overlook when they get really deep into type hinting is that it's not a static validation or verification technique. Type hinting is only a linting technique. There is no way for us to statically assert that the types actually match up in Python like we can do in C++ or Java. And so one thing that I encourage many of you to do is to change my mind about change my mind about type hints. And the way you can change my mind about type hints is as follows. Take a library of code that you have worked on, that somebody else mostly developed, that you're kind of confused about how it works. Try to refactor it, and try to use type hints in order to guide your refactoring. Presumably, if that's a helpful technique, then by adding hint annotations everywhere, that would give you enough understanding about how the code works, so you could then refactor it. But I don't think that you'll be very successful. I think that the typical technique of dynamic analysis via unit tests is what you'll have to do. Let me show you an example of why this kind of stuff simply doesn't work, and why we couldn't just go through the source code for matplotlib and say, well, if it calls core, let's just grep for core. Like, why can't we just grep for every function, then grep for every function call within those function calls, and then we'd have one flat file that says this function calls this, this, and this function has this argument, and then form a tree from that. Well, the problem is even very simple and common patterns will break this. For example, if they did g equals core, like this, and they called g, so any kind of first-class functions, any kind of polymorphism immediately breaks this. One important consideration when talking about things like static verification or static analysis of code bases is to understand what does the typical code base look like and what does a real code base, not some completely synthetic, like I tried to do the most complicated thing in the world code base look like, but a real code base like Matplotlib or Pandas. In my review for this talk, what I found is even a fairly normal code base like Matplotlib has enough oddities deep inside of it that simple techniques like simple grep-based static analysis simply won't work. However, one very nice benefit of code bases like Matplotlib and Pandas is they tend to have very large test suites and very large example use case suites. In many cases, those example use case suites are not complete, but they may be complete enough to exercise enough of the functionality. So if I told you, instead of attempting a static analysis technique, instead of attempting to read through the source code and try and figure out what passes to what and what the call graph is, what if we took the example test code that Matplotlib has? There's a million of those. You see them online. If you look in the matplotlib source code, you can see there's this folder here. And we can even say find name star.py and see how many there are. So it's 526 examples. These aren't even the test cases. These are just the examples. And if we wanted to, we could even see how many lines. There's 34,000 lines of example code. It may not be complete at exercising all of the functionality of Matplotlib, but it probably represents a good amount of what actually happens in a real Matplotlib code base with regards to how arguments are passed, what calls what. And we could maybe even, with some dynamic analysis techniques, try to identify what the code coverage is of the example test suite of all the possible modalities inside the library itself. Now, the problem is dynamic analysis techniques in Python, there's a couple of ways we can do this very easily, and there's a couple of really easy tricks that you can do to solve this problem of, I have a code base, I have no idea where to start looking, and I need a foothold. One of the common techniques that you might use is module import analysis. Now, I don't know if I have a good example of it for you because I have a better way to do it than module import analysis, but you may know that in Python, there exists this thing called, I don't know if I have a really good example. I don't know if I can write a really good example for you, but there's metapath in Python, and you might not know what sys.metapath is. What it is a list of objects that can intercept imports. And so when you actually import a module in Python, it actually uses this object here, this built-in importer, to identify, is this a built-in module? How do I import it? This frozen importer, is this a frozen module, how to import it? Or this pathfinder, is this a module that sits somewhere on my file system in some path, and load that. What we could do is we could take this pathfinder and we could either patch it or we could insert another import helper, another import hook in the middle here, and just say, when you try to import something, just record what you're trying to import and then build a graph from that. Now, during the question and answer session, I might be able to find one of these graphs that I built for a real code base. I don't have one offhand, but I've built these for real code bases where you can take a large code base and say, when you run this against a test suite, because this is not a static analysis technique, it's a dynamic analysis technique, it requires that you actually run some code somewhere. So you need to have a sample code base, either test code or example code. But when you run this against a test code base, this module imports this module, imports this module, imports this module, imports this module, and so on. Where do you think that could be useful? You want to figure out how to get started on this code base. You want to figure out how to learn it. Maybe the module that everything else imports is a good place to start. And when you look at a real code base, you often see that there's like a core, the meat, right? And then there's a bunch of leaves, just the bread surrounding that meat. And it's like, does anyone have a friend who, I have a friend who whenever you go out to eat with them and they get a sandwich, they'll take the bread off and just eat the meat. Yeah, so that's what you want to do when you're analyzing a code base. You don't want to look at all the, oh, this is how you do the configuration. This is how you do the file management. Oh, if the configuration file is not in the home directory, then look in this other directory. You don't care about that. You want to find the core algorithmic or model code. And often in a real code base, it's very difficult to find. But if you had an import graph, it might not be that hard because almost certainly the core algorithmic or model code is going to be imported by everybody. And at the leaves, there'll be the different applications or the different helpers or different utilities. And you can ignore those at the start. You'll also be able to see certain patterns, like are there modules that everybody goes through? Those might be configuration modules. Those might be some global state modules, and so you can get an understanding of that. Now, the way you do that is actually fairly simple. You just write an import hook, pure Python. You don't have to do anything too fancy. But there are certain limits to that technique, which is you can only look at what imports what. You can't look at what uses what. So if a module imported something and never used it, you'll get a little bit of noise there. For a real code base, maybe not a lot of noise, but for, at the edges, you might get a little bit of noise. And the net value of that for a very big code base may not be that high, because there are code bases that just don't have that heart, that artichoke heart worth of value, that are just smeared all over the place. Let me show you, or let me discuss briefly another technique you might use. Many of you may be familiar in the sys module with set profile. You can set profiling hooks in Python so that every time let me see if I can do this. So I'll show you an example. So every time I call a function, the profiling hook tells you when you called into a function, when you returned, and what I can do in my profiling hook, I get a frame and some other garbage, print frame.cocode.coname. Is that it? Anyone know? Nobody? Come on. Oh no, okay. We'll just figure out yeah. Thank you. Somebody's paying attention, that's good. So here's the code. No, it's the frame.code. Is it code? Okay, let's do this. We gotta figure out what it is. So, .f code. Very obvious, I should have known that. Worst talk ever. I should have gone to see what's the talk opposite. It's about neural networks. At least you're not in another neural networks talk. So at least we're having a little bit of fun. So let me just show you what this looks like. This should be the F code.
It was about drugs.
Oh, this one involved drugs as well. In its creation, maybe not in its presentation. So what you can see is when I call F, you can see you called into F, you called into G, you left F. So you can actually you can fairly easily get a call stack here. So let me print out one more thing. I'll print out the event. It's the event and then some other garbage. And you'll see that with literally 2 lines of Python code, the creation of the hook and the setting of the hook, for a call stack, you can see I called into F, I called into G, I returned from G, and I returned from F. So basically in about 5 lines of code, you could add this to your site packages, to your path, run your example code, and you could see this calls this, calls this, calls this, calls this, returns, calls this, returns, calls this. And you could use NetworkX and you could build a very simple graph from this. And so that would be another simple dynamic analysis technique that you could employ. The dynamic analysis technique would be what calls what in my example suite. And so just like you could identify the centralmost modules, you could identify the centralmost functions. And one thing that's missing, though, is none of these can solve our args or quarks problem. While you could look at the functions and you could grab the signatures from those functions and say, well, this one takes star args and star quarks, and this one takes ABC, and make some inference, you don't really know what looks at what. So I want to show you the technique that I employed. And it was based on something I did a while back called R-watches. And it's a fairly simple technique that took only about, that much code. It took me a while to get this code to work, and there's actually some duplication. All this stuff is just cut and paste 3 times. But what I did, it's not that hard. What I did was I edited basically 4 or 5 files in CPython, the most important one being ceval.c. And let me show you how Python works. Whenever a bytecode runs, like whenever you do a binary add, like you add 2 things together, Python pops the 2 things you're going to add together from the top of the stack. It makes a place where the sum is, and then it calls into some code here. Every time you need to actually, and I'll show you that, Python from dis import dis. So if we have a function that looks like this, and we disassemble it, you can see it loads 2 things onto the top of the stack, then it binary adds, and that pushes that there. If you look at the load fast, you can see what it does is it pushes something onto the stack So basically, every time you need to perform an operation on a Python variable, like add it or call it, use a function to call it, you have to push it onto the stack so the next operation can pop it off the top of the stack. Well, it turns out this push is a macro, which means we could override that macro with a fairly complicated macro that looks like this. And there's 3 versions of them, and I'll show you why. And what you can do is you can say, okay, can I set as a watch target that if the object that I'm pushing to the top of the stack is a specific ID that I want to keep an eye on, call a callback function. So just like in the set profile, I was having callback functions on the entering and closing of functions, here I can have a callback function every time your Python code looks at a variable. Not necessarily does something with it, but even looks at it. The moment it touches the top of the Python stack, it gets called. And the reason there's 3 of these, and that one's called push and this one's called watch, is I can also, in specific bytecode, watch specific events. So here, what I can do is every time you try to store a local variable, I just emit an event, have a little callback, where you can do whatever you want. With that, I can write some simple instrumentation code. I have my patch interpreter with about 50 lines of patch, much of which is cut and paste. And I have a very simple little thing here that when you, yeah, it's not that bad. You have a little stub, and when the stub gets activated, there's a couple of complexities that were added here because I'm doing this on every single push of every single Python variable. When I ran this on one example from the matplotlib test case, it generated 4 gigabytes of output data for a 100-line file. The example I'm going to show you is a 5-line file that'll generate about 3 megabytes of output data. But I have a big data problem, so thankfully this is a PyData talk. So maybe they'll ask me to speak next year. But the idea is, every time you see a variable get touched or looked at, you can record everything about that. What function was that variable looked at? What was the line number that touched that variable? What was the module? And you can generate an enormous amount of information. Now, I'll show you a simple example like this. Here's a simple example that kind of matches this quargs args problem. You have a function f that goes through f and then g down to h, okay? It had 3 arguments on the outside, and then it gets passed down the stack. And these could be in different modules. They could be all over the place. You might not even know which G this is because that might be dynamically determined. But if you run this code and you watch these 3 variables, you can see, well, ABC got passed in here, got passed in here, and got passed in there. What I end up generating is a fairly large JSON file with all of the times the variable is looked at. And this includes the entire call stack, the line number, the ID, and what the object's type was and what the repr of the object was. I also generate some other information, like the modules. These are all the modules that were imported in the process of running this. And the last thing I generate is these are all the signatures of all the functions that were involved. So I can do some fairly sophisticated techniques. Now, I didn't have time to put together a really nice analysis, but I put together a fairly simple analysis. And the analysis I put together says, given a particular variable that I want to look at, what functions did that variable get introduced into and get used in? So I'll show you this in practice, because I know I'm running out of time. So we'll run it here. No, it's in this directory. And you can see, even with a very simple technique like this, we can do that, and then this generates a dot file, and let's take a look. And this is the actual call stack for that ABC variable. I'll show you the example one more time. So that's what the example looks like. This is the call stack. You can see this variable was introduced in the main module and used in the H module. So what I could do to solve this quarks problem is, quite literally, I can run through the matplotlib example code. The problem is it's going to take like an hour or 2 to run each example. But I can run through it, and I can tell you exactly what arguments got passed in at the top, where did they get looked at, and I can infer from that quite easily that, look, this ABC was passed all the way through the stack. I know everywhere was passed, and this is where it terminated. It didn't get passed any further than that. In fact, if I change the code so that it gets used in G but not passed down, then I'll get a different graph that shows me where it was introduced and where it was used. This ends up generating a lot of data that needs some fairly sophisticated data analysis techniques because while there is a little bit of noise, there's a lot of inference that you need to do, a lot of heuristic inference you need to do to figure out how the code base worked based off of this. But the idea here is something quite simple. Through hacking an interpreter with some fairly minimal, fairly lightweight hacks. Honestly, the hacks that I did took about 30, 45 minutes to do. The hardest part of it was you have to be somewhat familiar with some pointer mechanics in the Python code base, but that's easy enough to just kind of read up about. But with some fairly simple hacks, I created a hacked interpreter, which then gave me significant instrumentation information that I could then run against a code base. Albeit, when I run against the code base, I get about a 60 to 100 times slowdown. But fundamentally, because this is an analysis technique that might be used to supplement documentation, it doesn't matter. It doesn't matter that none of you want to install my hacked Python. It doesn't matter that it's slow. Because if you think about the use case, what would the use case be? Once a month, before I do a release, I run against my hacked interpreter. I don't even have to keep the hacked interpreter up to date, because how long do you think matplotlib is going to support Python 3.7, right? When's matplotlib going to drop support for Python 3.7? Not for another 10 or 15 years. So I don't even have to keep this code up to date. I just have to make it run once. I can put any dirty hacks I need in there to satisfy weirdness in the matplotlib code base, run it against the code base, and start generating graphs, generating output documentation that could then be used to supplement, in an automatic fashion, supplement existing documentation. Here you can see an example of how this, you can imagine, could then be used to infer what the args and quargs actually are, what's actually used, and you could generate a very interesting kind of coverage testing from this, because you could see what arguments or what modalities exist in the code base that aren't covered by your example codes. You can also do some other interesting things here as well. If anybody here has user input feeding into their system, the reason that you put watch points on the additional bytecodes is you can do taint analysis. You can take user input, taint those objects. Every time they're used in an expression that gets stored to another object, you have the ability to look at when the computation for the result value is and when the store happens, and you can tie those together. So you can take a string. If somebody uppercases that string, you can propagate the taint from the original data to the new expression, and you can propagate the taint throughout the system. So you can say, this resulting value that I use in this critical part of my system was tied to some user input at the edges of my system, and maybe we need to make sure that it's sanitized correctly. So there's a lot of things you can do with very little code that's fairly hacky. And so I hope that was an interesting example of how these hacky interpreter techniques actually can, in some contexts, produce useful analysis of real code bases without you having to do a lot of software engineering or upstream things. Just throw some hacks together in your interpreter and see what you can do. Thank you.
Questions for James? Yeah, there.
I hope that was interesting.
Thanks for the talk. How much of this, if anything, can be done with debuggers, and can they possibly be extended to cover some of this so that we don't have to have hacky
So
interpreters?
the first way I tried to sell people on RWatch was that you could, if you look at the name RWatch, the reason it was created was to mimic RWatches in a debugger like GDB. In a debugger like GDB, you can actually tell GDB, this memory location, every time somebody reads from that memory location, break. So that you can see in a large system, like who's looking at this information, like a global variable, and you can track who's depending on that global variable. You can't do that in Python at anything but the interpreter level, because the only way to hook into that reading is by hooking into what gets pushed or popped or what gets involved in a bytecode. There is one thing that's missing here, which is once Python code goes into C code, everything becomes opaque, because you can't look through, the interpreter stack can't look through into C code. It's very opaque. What I thought RWatch would be interesting is as a debugger, a very slow debugger, but a debugger where you could do things like say, in my ETL pipeline, track this piece of data all the way through the pipeline and see where it goes. But nobody seemed to care that much. People seem to care more about args and quargs documentation really putting a crimp in their style. But yeah, I mean, this is essentially a debugging technique repurposed for code analysis.
Other questions?
Thanks. I was wondering, because have you ever tried creating a graph like this in a large code base and combining like all the different graphs to make one huge graph for the entire?
Yeah, I did about 15 minutes ago, and the problem is, it's possible. It's going to take more computing resources than I was able to put together for this presentation. So actually, in this example, you can look at all of the variables. in the analysis, I'll show you, it's a little bit difficult to read the graph without a little bit more work in the presentation of it. Let me show you what I mean. Here, do this and this. So we'll rerun this. And I'll show you, this is the graph if you look at every variable and the path of every variable. There's a good amount of noise here because there's a lot of variables you simply don't care about. Like this f and this g is the name of the functions f and g themselves, so you'd want to elide them. Now the point of this technique being hacky is that every code base will have certain things that you know for certain you don't care about looking at, and instead of generalizing that technique, which would be an enormous amount of effort, you just hack away. Don't look at a function if it's called f, don't look at something if it goes into this module. One problem that happens with the matplotlib code base is because of the way, if I remember correctly, because of the way that I was running it, some of the Python code for the site package import lib was generating at least a gigabyte of output data. And so all I did when I was trying to put that together was, if you're looking at a module call, a function call in the import lib module, just ignore it. Because I could in a reactive fashion look at my data, look at my code base and say, ignore this, this, and this, and only pay attention to that. Now, I don't know what this graph really tells you, since it's so large, but it does tell you something interesting. You can see the call structure, and you can actually kind of see things getting passed through from F down to H. And you can see that it gets passed all the way down, and you can see that G doesn't really do anything, because the only variables G looks at are this is the args tuple, the quargs tuple, and the function name. And that the actual function arguments, the A, B, C, the D, E, F, and the X, Y, Z, are only looked at in the F and the G. So you can begin to see in this larger example how the arguments flow through the system. And this is just one analysis you could do. I mean, presumably, if you wanted to play with this, and if any of you are interested in playing with this, what we could do is we could take my code, run it against a code base overnight, generate gigantic pandas data frames or CSV files or JSON data frames, like probably about a gigabyte each, and then give it to people and say, okay, what can you infer from this? You could probably even infer opportunities for optimization without too much difficulty. You could see repeated calls with the same input arguments, so you could see places where memoization isn't occurring, things like that.
Well, let's thank James again then.
Thank you so much.